So today we're pulling back the curtain on something that's all around us, but maybe we don't think about too much. How AI actually remembers. From the autocomplete on your phone to the smart speaker in your kitchen, these systems have to understand information in a sequence, and it all boils down to one crucial thing: memory.
I mean, you've seen this a million times, right? You start typing something like, "I'll be there in a," and bam, your phone just knows you're probably going to say minute. So how does it do that? Well, it's not magic, I promise. It's a very special kind of AI that's been built specifically to understand patterns where order matters.
And that right there, that's the core challenge we're diving into. It's all about understanding data where the order isn't just important, it's everything. You know, whether it's words in a sentence or notes in a melody, if you change the sequence, you change the entire meaning.
Okay, so there's a formal name for this, of course. It's called sequence modeling. And honestly, the best way to think about it is like reading a really good book. You have to remember what happened in Chapter 1 to understand what's going on in Chapter 10. Well, sequence modeling is just how we teach computers to do that exact same thing with data, whether it's sentences, stock prices, you name it.
So where did this all begin? How did we first teach a machine to remember things in order? Well, let's meet the original hero of our story, the recurrent neural network, or as you'll always hear it called, the RNN. This was the first really big breakthrough in handling sequences.
The core idea behind an RNN is actually pretty straightforward. It works one step at a time. So instead of trying to process all the data at once, an RNN reads one piece of information, creates a little summary of it, that's what we call a hidden state, and then it passes that little piece of memory along to the next step.
Let's make this really concrete. Say an RNN is reading "the cat is." First, it sees the word "the." It thinks about it, creates a memory. Then, it sees the word "cat." It doesn't start from scratch. It takes its memory of "the" and updates it with the new info about "cat." Now, its combined memory is basically "the cat." And with that context, it can make a really good guess that the next word is probably "is." You can see how that memory just builds over time. Pretty clever, right?
But, like in any good story, there's a plot twist. Our hero has a weakness. RNNs have a critical flaw, a kind of digital amnesia that kicks in when sequences get too long. And this big problem has a name: the vanishing gradient problem.
So, for a network to learn anything, it needs instructions on how to get better. In AI, we call these instructions gradients. The problem with the standard RNN is that the further back in a sequence it has to look for information, the weaker and more distorted those instructions get. It is exactly like that game of telephone you play as a kid. The message is a total mess by the end of the line.
And this distortion leads to two huge headaches. First, you have vanishing gradients. That's where the instructions get so faint, so whispered, that the model basically just stops learning from anything at the beginning of the sequence. It forgets the start of the story. Then, you have the total opposite, exploding gradients. Here, the instructions get so loud and chaotic that the model's learning process just completely breaks.
So this memory problem was a massive hurdle, a real roadblock for the field. But, as often happens, a big problem forced an even bigger solution. Researchers developed more sophisticated networks to solve this exact issue. And that's where we meet our next heroes, LSTMs and GRUs, the networks that got a serious memory upgrade.
Okay, first up is the LSTM. It stands for long short-term memory. And the genius of the LSTM is its architecture. It has a special memory cell, which is like a conveyor belt for information. But more importantly, it has these things called gates. You can think of them as little traffic cops that have total control over what information gets remembered, what gets forgotten, and what gets used.
This smart notebook analogy is just perfect. An LSTM isn't just passively remembering everything. No, it's actively managing its memory. It has a forget gate to erase details that are no longer relevant. It has an input gate to decide what new important information it should write down. And it has an output gate to decide what piece of memory it should use for its very next prediction. It's a truly dynamic system.
Now, the LSTM is incredibly powerful, but all those gates take a lot of computing power. They can be a bit slow. So what if you need that smart memory, but you also need to be faster and more efficient? Well, that's exactly why the GRU, or Gated Recurrent Unit, was created. It's a streamlined, lighter version of the LSTM that gets the job done with a little less complexity.
So let's put them head-to-head. The LSTM, with its 3 distinct gates, is your heavyweight champion. It's fantastic for super long, complex sequences where you need to track dependencies from way, way back. The GRU, on the other hand, combines a couple of those gates into one, simplifying the whole process. This makes it faster and more efficient, perfect for tasks where speed is a top priority.
Okay, this is all fascinating theory, but where do we actually see these powerful memory networks in our day-to-day lives? Let's connect all this back to the real world.
Well, their biggest and most common application is in helping machines make sense of our words. It's a huge field called natural language processing, or NLP, and believe me, it is everywhere. And this is where it all comes together. That autocomplete we keep talking about, that's text generation, often powered by an LSTM or a GRU. When you use a translation app, that's a sequence model figuring out the word order in one language to create a perfect new sequence in another. Even when a website figures out if a product review is positive or negative, that's called sentiment analysis, and it all relies on understanding the sequence of words.
But hey, it's not just about words. These networks are also masters at finding patterns in any kind of data that's collected over time, basically numbers on a timeline. This is called time series analysis.
Think about it for a second. Predicting stock prices means understanding past trends. Forecasting the weather involves recognizing seasonal patterns. You can even use this for medical monitoring, like looking for abnormal patterns in a patient's heart rate over time. In all of these cases, LSTMs and GRUs are the predictive engines running behind the scenes.
So, what's the big picture here? What's the main thing to remember? I think one last analogy is the perfect way to lock in the roles of these 3 amazing networks.
First, you have the basic RNN. Let's think of it as an eager but slightly forgetful librarian. They read every single page, but by the time they get to the end of a really long book, the details from the first few chapters have gotten pretty fuzzy. That's the vanishing gradient problem in a nutshell.
Then you have the LSTM. This is our expert librarian. They don't just read, they take meticulous notes. They know exactly which details are important to jot down, and they can easily flip back to their notes on Chapter 1, even when they're reading Chapter 20. Their long-term recall is almost perfect.
And finally, we have the GRU. This is our super efficient librarian. They've developed a clever shorthand system for their notes. They capture all the same critical information as the LSTM, but they do it faster and with less effort. They're streamlined for pure speed and efficiency. And that really brings us to the future. We've gone from a simple, forgetful memory to a smart, gated, and actively managed memory. And it's fundamentally changed what AI can do. It really makes you wonder, as this artificial memory continues to get even better, what complex sequences, whether in science, art, or even human interaction itself, will it learn to understand next?